numerous injuries, a cost of over $40 billion, thousands without homes, and nearly 200 lives lost. But there's a damage you can't put a value on. The grief, the hardship, the preventable losses. Although there are countless tragedies arising from earthquakes, this specific upheaval was caused by the Canterbury earthquake in 2011. Now, you may have heard of the Ring of Fire, and I'm not talking about the Johnny Cash song. I'm talking about the Pacific Ring of Fire, an area where a large number of earthquakes occur, and unfortunately, this zone runs down the length of New Zealand. In the past decade alone, the number of severe earthquakes that have struck New Zealand are in the double digits. You only have to look at Canterbury to see the considerable social and economic harm caused. What if I told you that the effect of future earthquakes could be mitigated? What if I told you that much of this heartache could be avoided? The sole reason that this groundbreaking technology has not been implemented yet is that earthquakes are a New Zealand problem, but most of our technology is imported from overseas. Therefore, we as a country need to take initiative and develop our own technology. An earthquake is a result of a sudden release of energy which generates seismic waves that propagate through the earth from the focus and transfer energy. The important difference between the two major types of waves are that P waves travel faster than S waves and cause no damage. Think of P waves as a propeller boat which travels fast but only displaces a small amount of water. Conversely, imagine an S wave to be a ship which travels slowly but displaces a large amount of water. If P waves can be detected, advance warning can be given before the vigorous shaking and damage occurs. Likewise, if you can spot the propeller boat before the ship arrives, you can prepare yourself for the large displacement. This will provide the crucial seconds required for a person to evacuate to safety. Depending on the depth of the focus, these seconds can range from anywhere between 10 seconds to 5 whole minutes. So where does piezoelectricity fit into it all? Piezoelectricity is a charge stored in a solid material due to the application of mechanical strain. This charge is stored as electric dipoles, which are pairs of equal and opposite charges separated by a distance. When you all came to this room, you chatted amongst yourselves and turned towards one another. This shows that without strain, the orientation of the electric dipoles inside a material are random, so the charges are able to cancel out. That is, you all looked in different directions. However, when the first presentation started, all of you turned towards the front of this room. This shows that when a strain is applied, the dipoles become reorientated from their random position, upsetting the balance of positive and negative charges. Since you all turned towards the front of this room, you could say that the front becomes positively charged, while the back becomes negatively charged. Now, to illustrate how common piezoelectric materials are and how easily they can be obtained, I've made my very own piezoelectric crystal from sodium carbonate and cream of tartar, both materials that can be bought cheaply from the supermarket. Another advantage of using piezoelectric materials is that they are very sensitive. This diagram shows individual atoms that have been moved around by a needle using a piezoelectric motor. So now I want you to imagine driving in a foreign country on a narrow road, and there's a small truck traveling in your direction. On the small truck, there's a sign that warns "oversized truck incoming," but you do not understand what the sign says. The P waves are just like the small warning truck that precedes the oversized truck, while the S waves are analogous to the oversized truck itself. The status quo in terms of earthquake technology developed so far is that we can detect an earthquake using a seismograph. When the ground shakes, The pen on the end of the sensor is free to move and draws on the paper like so. However, the nature of this technology is not adequate enough, so no advance warning can be given whatsoever. It essentially gives information about the size of the oversized truck after it has passed and forced your car off the road. The only merit of using the seismograph is to gain a better understanding of earthquake trends so that scientists can come closer to predicting earthquakes in the future. However, if I place some plasticine between the table and the sensor being proposed, the plasticine is squashed when the table shakes. This is analogous to an earthquake where the ground shakes, causing the piezoelectric material to be squashed. Traditional P-wave detectors, constructed using piezoelectric materials, are not sensitive enough to detect small P-waves. This is problematic because the P-waves are only large enough to be detected if the focus of the quake is relatively close to the sensor. If the focus is not very far away, the delay until the S-waves arrive is very small, so little advance warning can be given. Therefore, a more sensitive piezoelectric sensor must be developed to give a better analysis of the waves. A pressure sensor is made of material that's coated on both sides by a conductor. When the P-wave reaches the pressure sensor, the piezoelectric plate is squeezed, producing a reorientation of the dipoles in the material. This creates areas of net charge. Subsequently, a voltage is generated between the two metallic faces, allowing scientists to measure both changes in pressure and the frequencies which are experiencing the most shaking. By combing this information, patterns and anomalies are more easily established, so that earthquake predictions are more accurate. This is likened to using a translation dictionary to understand what the words oversized truck and coming mean. In technical terms, this sort of data processing is known as Fourier analysis, where some functions can be represented as the sum of simpler functions. Consider an orchestra with people playing the piano, trumpet, violin, and all sorts of instruments. The collective noise produced from these instruments could be graphed and would look something like this. In a concert hall, it is very difficult for you to distinguish one particular instrument from the others. An earthquake gives out a mass of signals, just like how an orchestra gives out many different sounds. Each instrument produces sound which is shaped like a sine wave, but has a different amplitude and frequency. Scientists only need to measure one type of signal to gain a better understanding of earthquake trends. By developing a more sensitive piezoelectric sensor, scientists will be able to distinguish between these instruments and the signals of an earthquake. Although using a translation dictionary may be effective, why not just spend some money and hire a translator? When the ground shakes, causing the piezoelectric rock to be squashed, a voltage can be detected through the use of a piezoelectric sensor. But notice what else can be observed. You can actually hear the shaking of the earth. In real life, an earthquake does not emit sound waves, but electromagnetic waves. This leads to the suggestion that better technology could potentially be developed that would be more effective at predicting earthquakes. When piezoelectric crystals in the rocks are squashed, the dipoles become reorientated. This would send out an electromagnetic wave, which is relatively weak with a frequency of 1 Hz to tens of kilohertz. Local receivers tuned to this low frequency range would be necessary to pick up the signal. The receivers would function much like the antenna on a car. However, it would be significantly larger, and instead of pointing to the sky, the receiver would point towards a piezoelectric rock. Prior studies suggest an increase in the intensity of low-frequency waves before the S waves arrive, so this knowledge can be applied to analyze P waves. If these two sensors can be used in unison, they can add increased accuracy to the detection of P waves and prediction of future earthquakes. Also, since the application of piezoelectric materials is already established in other industrial and research fields, the cost of investment is relatively low. In essence, the receiver is the translator which decodes what the sign is saying, allowing us to better prepare for the oversized truck. Now, the main benefit of predicting earthquakes in New Zealand's future are social. If people know when an earthquake is likely to strike, they will be better prepared, which will minimise the deaths and injuries caused. However, the value of this idea comes from the ability to detect tectonic hotspots where earthquakes may occur in the future. This will allow buildings to be strengthened or constructed to a higher standard in these earthquake-prone areas. Consider the Canterbury earthquake. The fault line that ran through the area was unknown before the actual earthquake, and most deaths occurred in 1 or 2 tall, unsupported buildings. Although you cannot put a dollar value on a human life, you can make a quantitative measurement of people's contribution to the economy. Severe natural events often precede a recession, so minimising the lost productivity from earthquakes is essential to maintaining New Zealand's economic well-being. The situation in Wellington is an example of this, as buildings are constructed to higher standards and extra precautions are taken, such as securing hot water cylinders to walls. This minimises the resulting burden on households, businesses, insurance companies, and the government. In heavy industries, advanced warning would allow hazardous materials to be secured and expensive equipment to be shut down to avoid environmentally costly spills and pollution. Although New Zealand is nuclear-free, the Fukushima nuclear disaster illustrates the devastating environmental impact that these industries may have. The outlined benefits amount to millions of dollars to the New Zealand economy, and significantly more if exported. Every day we delay, there's a potential for more tragedy. When will the next big one occur? Only piezoelectricity will tell. Thank you.
Thanks, Andrew. I like the analogy of the oversized truck. Is there a correlation, and if so, what is it, between the strength of the P wave and the strength of the S wave?
There's not really a correlation between the two. The P waves precede the S waves, so...
Yeah, but do the P waves give any indication of the strength of the earthquake itself?
Well, we can graph the waves produced by the P waves on the piezoelectric materials, and by judging the amplitude and frequency of the waves, we can judge the strength of the earthquake.
So there is a correlation?
There is, yes.
If you wanted to identify the Christchurch fault line which led to the earthquakes before the earthquakes happened, how would your piezoelectric sensor have done that?
Well, so there's 2 different types of sensors, as I explained. But for the second sensor, that's the radio receiver.
The radio receiver.
These will be placed in positions all around New Zealand because piezoelectric rock, such as quartz, is already abundant in natural reserves, and the receiver itself is not very expensive, just like the cost of an antenna. So if we place lots of this technology around New Zealand, where there are deposits of piezoelectric rocks, we can detect if there's any unusual activity which may suggest that there's a fault line.
Just give me a rough idea of how many of these receivers you're imagining would make a difference.
Perhaps 1,000 of those radio receivers, and for the pressure sensors, it will be considerably less because only several are required for each fault line.
All right.
But as I emphasised before, the cost of both these sensors are relatively low, so there would not be a major burden on the government.
Going back to your piezoelectric material, your sensors, the maximum warning that would be able to give people is 5 minutes. Is that what you said?
That depends on the depth of an earthquake. But if the depth was, say, 500 kilometres, 5 minutes would be correct. However, 5 minutes would still be ample time to, for example, get out a doorway or evacuate outside of a building. But I want you to understand that the main benefit of using this technology is to detect tectonic hotspots where future earthquakes may occur. So it's not a short-term, like, oh, there's an earthquake coming, we have to evacuate. It's a long-term plan. We know that this place is earthquake-prone, so we need to construct better quality buildings there.
Thank you, Andrew.
Thank you very much.